we're going to look at some guarantees to the general adaptive form. The focus will be on adaptive algorithms that are traditionally found in areas of applied signal processing. The analysis method will be based on ordinary differential equations. And this method was formulated from a general view of recursive identification, and certainly long after Robbins and Munro proposed their update equation. So one of the tricky aspects of constructing this presentation, particularly for a study group, was actually finding a good place to start. So in presenting the theory, I've attempted to be, I guess, somewhat heavy-handed on the application side of things. So the ODE method will be presented along with application to two areas of signal processing: equalization of an unknown communications channel, and also active noise control in audio signal processing. So today, what I'll do is I'll derive a suitable algorithm for the equalization problem, and then I'll present the ODE method and the main theorems. And then next week, we'll discuss how the theorems are applied to the algorithm. And I'll also apply the ODE method to the active noise control problem, which I hope will reinforce some of the intuition around the method. So let's start. So we're looking at analysis of adaptive algorithms and a particular approach to verifying asymptotic convergence called the ODE method. So I guess so based on the few presentations we've had so far, this adaptive form that you see in front of you may, or hopefully is starting to look a little familiar. So we have a general form. This is a general form of the parameter update equation that's used in many adaptive algorithms. And we'll see how special cases of recursive identification are derived from this form. Now, one observation that may help set the tone for this topic is, well, first of all, you recognize that there's a correction term here and a gain term. And if you place this previous estimate of the parameter onto to the left-hand side, and you were to say, hey, that looks like this now looks like a little bit like a difference equation, then you actually wouldn't be drawing a long bow. So just explanation of some of the symbols. So theta is the parameter vector of the model of the system, or the particular part of the system that we wish to identify. Capital X is a state vector, and this is how new information enters into the update equation. And its form is determined by the model set. And in this discussion, we'll talk about small gains, and we'll see why this is the case. But in rough terms, small gains help keep the solutions tightly bound. And now capital H is the general form of the correction term, and it has a Markov property in the sense that it depends on previous parameters of the current state. And embodiments of H will depend in part on the notion of search in the adaptive algorithm. So that is whether we're using gradient descent or a Newtonian method. And discussion of the perturbation term is beyond the scope of this talk, but not to diminish its importance, but we'll sort of conveniently ignore it for the remainder of this presentation. So the difficulty of the analysis of the general adaptive form lies in the fact that the difference term is dependent on previous values of the parameters. Now, we could simulate the algorithm to understand its behavior, and this would be perfectly fine, were it not for the fact that this simulation is specific to instances of the problem. And the objective here is to introduce a method that has general applicability. Simulation is important, though, for studying aspects of transient behavior and convergence rate and finite sample properties. So it's useful alongside a general analysis method. So the approach is, here we've got a classic case of taking a problem that appears to be intractable, and what we do is reframe it in terms of another problem that is well understood. And so in this way, we might infer properties of the first problem with respect to the second problem. So to that end, if we can, the idea is if we can rigorously prove an association of the ODE, then convergence properties of the ODE can apply to the algorithm. And we'll make some heuristic arguments demonstrating why this is a reasonable thing to do. So with that said, I wanted to jump into our first application. So this is the first of two real-life problems that I'll present. So here we have an identification problem that has a fairly simple model and can be solved using the general adaptive form. Message A, or symbol A subscript n, is transmitted over a channel, and the channel is unknown. And the objective here is to estimate A subscript n hat by filtering the noisy observations y of n. And so the objective is to design an inverse model of the channel theta that gives a low error rate for A hat. And so theta in this application is called the equalizer. Now there are at least two objectives to the identification problem. In the first objective, we're learning the channel, and so we're seeking to identify the parameterization of the inverse channel. And in the second problem, this is where we might want to continuously track changes, parameter changes that can occur due to external influences, for example, atmospheric effects and whatnot. There's a third phase, which is called blind equalization, in which the channel cannot be learned. And this might be a case in, say, broadcast systems where receivers may be acquiring and releasing the channel. And therefore we can't sort of interrupt the channel in order to relearn it. And so the blind equalization in the adaptive system uses a function of the equalizer outputs instead of a training sequence, A subscript n. So we'll mainly be talking about the first problem, the learning phase. We'll touch on the second problem, but we won't be discussing the third problem. So in system identification, there are a number of design tasks, and we'll introduce what's necessary for designing an adaptive algorithm for the equalizer. So first of all, we need a model for theta. Without going into all the possible choices of filter, we'll opt for a transversal all zero form. And if you're familiar with finite impulse response type filters, then this is essentially one of those. And it gives the output of the equalizer as a convolution of the filter and state. The presentation is not about model design, but it's worth qualifying the choice here. First, it goes without saying that the model should be chosen to best describe the input-output characteristics. The FIR form, being a linear system and a homogeneous function of time, means that it's fairly robust. And I mean robust as in stable, and stable for a limited class of channels. There's other models which are based on rational transfer functions, and they require, I guess, considerations of stability in asymptotic convergence. And we'll touch on this point when talking about some of the general requirements for the model set. But our choice of using an FIR filter also implies that the model changes are varying slowly in time. We should also talk about the properties of the input signals. So if you remember back to the diagram, we have a signal V, which is the source of stochasticity in the model. It's assumed to be IID, and then there's the symbol set, and the symbol set is designed to have a uniform distribution. Primarily, we want the signal model to be asymptotic in distribution. This is not only a requirement of the theory, but there's actually also a practical advantage, and that is the uniform zero mean nature of the symbol set also improves bandwidth utilization. So how do we know if the estimates of theta are any good? So given a set of parameters defines a particular instance of the transversal filter, the validity of that instance can be measured from the estimation error. And therefore, the variance of the estimation error defines a suitable criterion for evaluating the parameterization. And of course, the objective is to minimize this criterion. So a solution to minimization problem can then be attained by setting the derivative to 0 here and solving for theta. And doing so gives the following optimal value. And now this is where we run into a problem. So we actually can't take the expectation here because it requires a joint distribution of y of n and also the symbol set a subscript n. Now we can observe values on both sides of the channel, but we can't know their joint distribution without knowledge of the channel. And that's of course the thing that we're trying to estimate. So how do we get around this? Well, one way is let's say we have a sequence around a variable, say x subscript n. And in this sequence, the sequence is drawn from the same distribution. And now also suppose that we're given a function f, and for some value of parameters theta, we can construct the function and evaluate the sequence. In fact, this is kind of similar to the news vendor model that was presented a few weeks ago. And you can think of, in this case, as f as the cost, theta is the order number, and realizations of x as the demand. And so now what we can do is find a solution to the following equation in 9. So applying this idea to the current model, x are the observations, which combine the reference and the output. And then we choose f as the gradient function. And then after sampling from the distribution, we can evaluate f. Then it remains to decide how we update the parameter vector. So one option is to repeatedly sample from the distribution and infer the solution, but it's actually more efficient to update the parameter vector on each observation. And so a recursive update that we attribute to Robbins and Munro is we show here in equation 12. Now, intuitively, you can think of this approach as utilizing information in each sample as it arrives. But you should be aware that in this context, the parameter sequence might then follow a fairly inefficient path to the stationary solution. So here we have, so using the Robbins and Munro equation, and combining with our gradient, we have the following adaptive algorithm. So just to reiterate, so there's no offline gradient estimation that we make from repetitions of the data. This is a sample by sample update equation. And you might actually be familiar with this. It's actually least mean squares algorithm, or LMS, arguably the greatest algorithm of all time. Now we have a specific implementation of the general adaptive form. It seems it's a good point to now review the ODE method for a convergence analysis. Okay, so the ODE method. As we've mentioned, the analytical approach to convergence analysis is difficult because of the difference term. The difference term being dependent on past estimates of the parameters. So in the general approach, we associate the differential equation with the adaptive form, and then what we do is frame the analysis in terms of the ODE. So some conditions on the quantities of the general adaptive form will first need to be established. Firstly, the nature of the gain term. So objective is to estimate fixed parameters representing the inverse of the unknown channel. And so for that, we'll need a decreasing gain. We need a general description of the state vector. So many state vector representations can be derived from a Markov chain. And this includes a special case of for our purposes, which is that the state is independent of the parameter vector. And thirdly, we need to place some conditions on the correction term H, which we'll call the vector field, and establishing an association between parameter updates and the trajectories of theta in the ODE. So I just wanted to make a sort of a heuristic argument to give some intuition behind the method. So if we take the update equation, we consider a sequence of n updates. So that just involves applying the recursion to the nth update. So we've made the gains, gamma subscript m, a small constant. So firstly, that allows us to omit the perturbation term. You might recall from equation 1. And it also allows gamma to sit outside the summation. And so in the first approximation, we assume that the previous n steps, in the previous n steps, theta belongs to a small neighborhood. And we assume that the algorithm has basically progressed far enough that subsequent changes in the parameter are small. We assume the state vector is, well, we know that the state vector is independent of theta, and the measurement noise, of course, is IID. So it's actually reasonable to assume that the state vector has a stationary distribution. And then finally, if n is large enough, then what we can do is replace the sum with an expectation. So these are justifications that are basically made, but there's just some additional comments that I wanted to make. At first, the theory requires regularity of H for association of the ODE. Some conditions placed on H, such as, so we can make H, for example, locally Lipschitz. And this weakens the assumptions around the state vector. But the nature of the regularity really depends on the assumptions that are made, and there's Jung uses some slightly, has some slightly different assumptions, and then Benveniste uses some different assumptions. So you can kind of weaken the assumption on the state vector either way, and then impose them on H. But the point is that H needs to have sufficient smoothness. And finally, points 2 and 4 in conflict. So the need for n to be small so that theta remains small in this neighborhood conflicts with the need for n to be large so that we can apply the expectation. And this conflict's resolved by having this small gain value. So as a result of the approximations, we now have a mathematical form that is similar to a difference equation with the index of the different terms defined by multiples of n. And so the question is one of now, how do we interpret the update equation as a continuous ODE that is shown here? And the answer seems to lie with this idea of concept of small gains and a smooth edge. So if we simply express the approximation from from equation 15 on the previous slide with the form of the ODE, then we have this update equation in equation 18. So here, theta subscript n, or the parameter updates, are equivalent to the ODE theta, but now we have the ODE has a new concept of this time index as shown here. And so this essentially is the idea on the connection with this is the connection with this notion of ODE time. And we can actually further extend this notion for variable step sizes by shifting the gain inside the summation. Now, this is not a rigorous treatment of the analysis, but for these reasons here, I guess it isn't a stretch that the ODE and the difference equation can have some equivalence. So let's give some more precision to some of the key quantities so that we can strengthen this argument. So our state vector is an independent variable. It doesn't have any theta dependence, and so asymptotic stationarity and regularity are easily satisfied for the learning phase, the transversal equalizer. But the question remains why we would need these conditions for other models. And so for that, we need some background on the form of the state vector. So algorithms in system identification exhibit dynamics that can be discontinuous and noise that is state dependent. So in our example of the model of the state vector, we can actually extend this model to capture dependencies on previous symbol estimates. And therefore stationarity is, in that case, stationarity is then tied to model stability. So for example, the analysis of recursive algorithms in Jung's original paper refers to the following case of the Markov representation. And we can see that the stability of this model is actually now dependent on A, and in particular, its eigenvalues need to be strictly inside the unit circle. So 21, the previous equation of state is based on linear dynamics, and it's a special case of a more general representation of the state vector in which X is a function of a Markov chain which is controlled by the parameter. So here we introduce chi, which is an extended state, which is also Markov, and chi captures the nonlinearities of the system. So this basically says that sequence of state vectors X are a function of these Markov chains, function of chi whose values are inferred from the chain. And this is useful in for self-tracking algorithms in which we might need a recursive model to deal with, say, the quantizer nonlinearities in symbol reconstruction. So therefore, it's a requirement that the state vector has transition probabilities that are regular and asymptotically stationary. And this means that well-behaved dynamics will result from this stationary transition probability. And then the regularity condition avoids transients that break recurrency in the Markov chain. So this leads to a minor theorem from the Benveniste text, which kind of captures the underlying importance of the Markov representation to stochastic approximation theory. So it allows conditions for the theory to hold under some important transformations. Now, the Markov representations of state goes, it's a little bit beyond the scope of this talk. And but I just wanted to kind of footnote this as a way of marking its importance, and it's quite central to topics throughout the Benveniste text. Also, just to recognise that the linear conditional dynamics model that was, when Jung wrote his paper, was actually the most general case presented, and so that things have moved on a little bit since then too. So the nature of the gain, well, the gain is decreasing in the learning phase, and there's we have two conditions. One is the speed of decay that's given by some alpha, and then the second assumes that we never quite reach zero gain, but this allows us to get arbitrarily close to the limit. So in other words, these conditions are basically saying that we're paying less and less attention to the noisy observations, and thereby rejecting them. In contrast, if we say we wanted to track parameters of a slowly varying system, then we wouldn't want the gain to go all the way to zero. The requirement here would be for some empirically selected small constant gain. So we don't want any sudden changes in the parameter vector and then run the risk of leaving our region of convergence. So we expect theta to vary slowly, and this imposes some requirement on the smoothness of H in terms of the following definition for the mean vector field. So the evaluation of this mean vector field requires us to freeze the state and parameters. In other words, the mean vector field is then an estimate of the current trajectory of H. An interesting outcome of this formulation is that H as a function of theta can be discontinuous, since the regularity condition only applies to H averaged over the state vector. And so this concept of freezing the parameters is key to actually evaluating the mean vector field in connection with the ODE. So just to give a summary of the conditions for the ODE methods. So we have, first of all, we have a general adaptive form for which the theory applies. We have a state vector, x, that's stationary and independent of theta. Estimating the fixed parameters of the model requires a decreasing gain. And then existence and regularity of the mean vector field as defined by the expectation in the limit as n goes to infinity. So with that, we can state some fundamental theorems. So the first theorem concerns the nature of the association between the update equation and the ODE for a finite number of updates. And so what this is saying is that it's basically saying that with the probability increasingly close to 1 and for a small gain, the parameter updates follow trajectory theta of t of n of the ODE, and that there's an uncertainty that's never greater than some arbitrary a priori value. And so in this respect, this gives uniform convergence in probability. And so if you were, the implication is if you're an engineer and you're designing an adaptive algorithm, then this is the result that you care about. So, you know, if you've set all conditions right, if your design is correct and meets the conditions, then you're guaranteed of convergence. Actually, something to think about is where the idea of a cylinder enclosing all the trajectories comes from. This is an assumption that appears in the Benveniste text, and the best visualization that I could come up with was a kind of trajectory which follows a helix on the cylinder. So in a cylindrical coordinate system, capital T, we say, would be the length of the cylinder, and then the initial condition would be defined by, say, a particular radius and angle at the origin, theta, or initial condition theta of naught. So yeah, I'd actually welcome any other interpretations on this. So the mathematician, however, would be interested in the infinite horizon. And so in this case, we need the following condition for decreasing gain. So the first condition here ensures that the variance of the parameters tends to 0. And then the second updates the algorithm to the limit. In fact, we can actually now say there's a trade-off between condition 1 and the smoothness of H. So that is gamma, or the gain satisfy condition 1 for some particular alpha, and then this determines the bounded moment of H. So in other words, the derivatives of H can't jump or cannot jump around too much with theta and X. So in practice, one would only choose a flatter, more aggressive gain profile if H were relatively smooth. And then a sharp contraction, say, in the gain values would be more appropriate for tolerating high variance in the noisy vector field. So let's also formalize this notion of the domain of attraction. So this is the case where n goes to infinity and it is assumed that the ODE is asymptotically stable. So it has, in other words, it has an attractor, which we'll call theta star. And the domain of attraction, d star, is then the set of all initial conditions z, where theta of z and theta of zt all converge to this attractor theta star. So the main theorem will be given. I'll give the main theorem for the case where the gain is decreasing. And the other point to make is that all of the conditions that we've previously mentioned around the state vector and the mean vector field are now also satisfied in this domain of attraction d star. So the second theorem for the infinite horizon, so the emphasis here is on establishing a connection between the parameter updates from the adaptive algorithm and the trajectories of theta of the ODE. So what part one says that, part one refers to a special case of error control with respect to the unique stationary point of the ODE. And then part 2 gives control over the error with respect to the ODE itself. So one interpretation is that here we have a scaling of the gain sequence gamma such that theta stays arbitrarily close to the domain with some arbitrarily high degree of probability, and that is the domain within which the trajectories of theta will remain. There's a couple of risks to diverging theta. So any situation where we have a runaway theta, this is indicative of some pathological behavior of state. So for example, theta may actually be stable in the domain, but the recurrency of the Markov chain has been broken. And the second is related to the boundedness condition. So the correction term may be too large and then cannot be reined in by the small gamma. Also the noise in the correction term, which is the difference between H and the mean vector field, can also increase to an extent that you get this like it's possible for a random walk to infinity to take place. This seemed highly unlikely. I kind of think about this one as like the black swan event, but I'd be interested to see an example of this in practice. And to my understanding, there's no general result that gives conditions under which theta is bounded. And as far as I can tell, it looks like the boundedness condition can only be verified for each algorithm. So a summary I actually kind of like this. So this is actually a good summary of the theorems of the ODE method. It basically says that, well, as it says here, basically after a transient phase, then the behavior of the algorithm is then represented by a first approximation by that of the ODE. What I might do is, so that's actually about halfway through the slides. I was anticipating maybe discussing next week a guide for how to apply the theorems to analysis, and then apply that, apply that guide to the equalizer, and then also talk about the active noise control problem. So, so Victoria, I'm happy to. This might actually be a good place to stop, and then just see if there's any questions or discussion on what's been presented so far. Finished off last week. The summary of everything we looked at basically is stated here. So after the transient phase, the behavior of the general algorithm is represented to a first approximation by that of the ODE. So, so how did we get here? Well, we made some heuristic arguments as to why it's reasonable to associate an ordinary differential equation with the general adaptive form. And then we developed two important theorems that associate the ODE with the general adaptive form for recursive updates in the finite horizon and the infinite horizon. And then as a backdrop, we also derived an LMS, least mean squares algorithm for the transversal equalizer. And so this week I wanted to focus more on application of the theorems to describe the convergence behavior of this algorithm. And I'll also derive a similar algorithm for a different problem to which we can also apply the ODE method. So, so quick recap. So we've established that the general adaptive form can be analysed in terms of an ordinary differential equation. So let's just revisit a few details of the result. So firstly, we talked about the conditions that need to be placed on the gain, the state vector, and the mean vector field. And so with these conditions, the parameter updates can only converge to stable stationary points of the ODE. And the limiting behavior of the LMS algorithm is stationary. And this is inherent in the design, but it's actually important to remember that in more general cases of adaptive algorithms, for example, where the state vector is recursively updated, that the limiting behavior is not always guaranteed. So any lack of convergence in this case may indicate an unstable quality to the design. Point 3 here is actually a proof of convergence. Where possible, if we can identify a suitable Lyapunov function for the associated ODE, then we can demonstrate global stability. And note that numerical solutions of the ODE also can also give one a valuable insight. So let's now apply these algorithms to the learning phase for the transversal equalizer. So in his original 1977 paper, Jung conveniently provided a guide to a application of the main theorems, and we lean on that guide quite heavily here. Now, since the theory has been developed for the general adaptive form, first and foremost, the algorithm under study must fit this form. And so to that end, we need to identify the vector field, the gain, and the state. And although it's not required for the learning phase of the equalizer, the residue and the extended state, which we briefly mentioned last time, they may be essential and need to be considered as well. We need to establish whether the gain is decreasing or constant. For example, if we're in the learning phase, then we'll need a decreasing gain. But if we're in a self-adaptive phase, then we need a small constant gain. It'll also dictate the size of the gain. For example, convergence heuristics for constant gain basically say it needs to be small. And often the choice of gain may be empirical, there's certainly many answers. And in fact, the art of selecting gain profiles for adaptive algorithms has spawned a whole field of research in itself. Again, not an issue in our case, but one should be mindful of any theta for which the Markov representation of the extended state blows up. For example, in a linear conditional dynamics model, one needs to ensure that the eigenvalues of the matrix A are in the left-hand plane. Another question is that should be asked is, does the extended state have stationary asymptotic behavior? Now, since we have an independent state variable, x, then we can basically combine points 3 and 4 into a requirement for weak stationarity. In step 2, we calculate the mean vector field. Actually, this is a good point to remind ourselves why the concept of the mean vector field is central to the ODE method. And the reason is that it defines the ODE by smoothing random fluctuations that obscure the convergence characteristics. So in obtaining the mean vector field, generally what we'll do is freeze the state and the error vectors. And then the calculation of the mean vector field can proceed based on the specific implementation of the vector field in the algorithm. Then the final stage involves study of the ODE. Now, we may be able to obtain analytic convergence results for the ODE directly from a classical stability analysis, or we could simply perform a numerical analysis of the ODE to inform the algorithm behavior. So classical stability analysis is preferred. For example, if one can find a suitable Lyapunov function for the ODE, then that'll guarantee stability, but it's not always possible to find such function. And this will become a little clearer in the following examples. So let's apply this 3-stage analysis to the transversal equalizer. So first, we reminding ourselves of the expression for the general form. We have a gain sequence that's a sequence of decreasing gains, since we are in the learning phase. We omit the perturbation term, and therefore we're left with the state vector and the vector field, which were previously derived as shown here in equation 36. Since we're using a transversal all zero model, then the state vector is independent of theta, and therefore it's asymptotically stationary. And H is regular under a locally Lipschitz condition. And so with these conditions they're satisfied for all theta. So we have almost bounded theta. So in stage 2, so we're evaluating the mean vector field, and that's according to our definition. So expectation of the vector field as n goes to infinity, and this will involve a freezing of the parameter vector and the state. And note that the asymptotic stationarity of x is also essential in obtaining the mean vector field. And then in stage 3, we study the ODE. So what we'll do is try and find a suitable Lyapunov function. And if that exists, then we can assert a global asymptotic stability. So the analysis in this case is quite straightforward. I'll give a little bit more background on Lyapunov stability theory in the next example. But here it should be easy to see that V in this case is the mean squared error between the true message and the output of the equalizer. And so therefore it's convex and bounded below. in other words, it's a decreasing function. And so therefore the stability theory tells us that the trajectories of the ODE must converge on a stable point. Sorry, just a couple of additional comments. So this is the case for the infinite horizon and small constant gain that was described in the Benveniste text, for which I used for this example. What I couldn't actually work out was if this result holds for the decreasing gain, and my guess was that it should, since the theorems for decreasing gain case, in those theorems we actually have control of the error with respect to either the attractor or the ODE. So, with that sort of simple example, I just wanted to move on to talk about a second application and apply the ODE method there as well. So, ANC stands for active noise control. And so in this diagram here, we have a typical feed-forward ANC system that's used to cancel a broadband noise source at position C. So most solutions of this problem use an error microphone that's positioned as close to C as possible to drive adaptation of a transversal filter. And this response of the filter is such that an anti-noise is generated from the detector signal and used to drive a loudspeaker. And so that the response of the loudspeaker at point C is ideally the noise signal of equal magnitude and opposite phase to the original noise source. Now there are two paths here. There's a primary path, which is the air path from the detector to the error microphone. And there's also a secondary path, which is this electrical path from the detector to the error. I like to think of the ANC problem as two sub-problems, prediction and equalization. So in that secondary path, there's actually a time delay that must be compensated. So, sorry, just going back. Basically, this filter needs to converge and generate the anti-noise signal in a limited time frame, that is before the broadband noise source actually reaches point C. So the control as such is therefore, it's a predictor of the sound pressure level of the acoustic noise. The secondary path also includes, so in practical cases, it'll include a digital analog converter, there's a reconstruction filter, power amplifier, and of course the loudspeaker. And those components, the cells will contain nonlinearities and some unmodeled dynamics. And these need to be equalized. So by introducing an equalizer, we can obtain a more uniform secondary path, a more uniform secondary path frequency response. Let's have a look at that in a more clearly with a control diagram. So this is the control diagram for the feed-forward ANC. Transfer function P here is the speaker to error microphone transfer function. So this is the problem for LMS type adaptive filters. And the performance of this system essentially relies on the coherence between the reference and the error signal, and the electrical delay through the secondary path, therefore, it cannot exceed the acoustic delay through the primary path. Otherwise, it won't be properly modeled. So one option is to compensate P with an inverse filter. But what we show, or as Widrow actually showed, that an estimate of P in the reference path to our adaptive, the LMS algorithm, can provide improved response in the presence of this of the unmodeled dynamics. And this is generally preferred approach. So you'll find most solutions will use this general style of algorithm. The other symbols here are, okay, so C, of course, is the controller that we're designing. This models the noise path G using a transversal all zero filter. And VK is the measurement noise. And in a lot of text, you might see this as referred to as the plant noise. And this is our source of stochasticity. So they're the symbols that I just described. So as I mentioned, we'll opt for the simplest model here for the forward path by using a transversal all zero filter or FIR filter. This is actually its popular choice for many implementations of ANC. And so C then becomes the parameter vector that is recursively updated. This would be equivalent to theta in the general adaptive form. So again, we will minimize the squared error criterion. So from the control diagram, we can infer the error vector. It's comprised of the transmitted noise source, the measurement error, and then the output of the secondary path. And so the input to the actuator, or the loudspeaker in this case, is the response of the reference signal to the forward path model. Now we can minimize the quadratic criterion. The error gradient that is, it can then be evaluated from equation 40 on the previous slide. Now, you might notice here that the gradient term is actually the convolution of the state vector delayed by I samples with the secondary path model. And so as the algorithm's namesake suggests, we have an error gradient that is a filtered version of the reference signal. And again, we use a Robbins and Monroe style recursive update equation, and substituting the error and gradient terms, we arrive at equation 45, which is known as the filtered X LMS algorithm. Gamma is our usual gain term. Also note that we actually don't have access to P, the secondary path model. So one option is to, so I've shown it here with a hat, just to say that it's an estimate. One option is to estimate it offline, but there are other ways of modeling the secondary path, and actually this remains an active problem. So we have an algorithm that fits the general adaptive form, so we can therefore apply the theory. So to recap, the remainder of the analysis is as follows. We first fix the model parameter. Okay. So so we're going to apply the ODE method, the guide to application of the method to the ANC problem. So so you might recall from last week that I touched on this idea that that balance exists between the restrictions that we place on the vector field and the error. So, for example, we can weaken assumptions on the error behavior in favor of a smoother vector field. And the theorem tells us that this is the theorem tells us that this is a degree of the gain scaling. So the algorithm therefore hinges on this kind of symbiotic relationship between the gain and the vector field H. So for example, that is a combination of the small gamma sequence and the regularity of H. So for the purpose of this discussion, we'll establish that the condition for H is that it is Lipschitz continuous in X and theta. And this amounts to a twice differentiability of H, which of course is satisfied for the filtered X LMS example. Note also, implicit in the method is the boundedness of theta, which is essentially a restriction on the stability region. It doesn't apply a restriction on the system dynamics, and I'll provide a bit of further direction on this at a later point. Next, we freeze the trajectories, as shown here. This is fairly straightforward for our case. In step 2, the average update term can now be evaluated by direct substitution of the frozen values. In the second line here, we've actually made use of the requirement that the plant disturbance and reference signal are uncorrelated. And finally, another substitution of the mean vector field into the form of the associated ODE will give the following equation, from which we can obtain a unique equilibrium point, and that is the point at which there's no further change in the parameter estimate. So the term undergoing inversion here, of course, it cannot be singular, and this is generally the case if the reference signal is sufficiently interesting from in a physical sense. Interesting in a mathematical sense means that there's a low eigenvalue spread on this matrix. So now we have the mean vector field and a definition for the associated ODE. We can use the theory to study the algorithm trajectories in terms of ODE stability. So at this point, we could numerically simulate the ODE, but there's some nice theory that we can apply here if we can, of course, find a Lipinov potential function for the ODE. So I'll give the highly abridged version of Lipinov stability theory. So a Lipinov function is a positive function that is decreasing as shown here in 51. So essentially its time derivative is negative. Now, remember the stationary point represents an equilibrium solution of the ODE as t goes to infinity, and we'll call the collection of such points the invariant set D subscript C. And also the invariant set has a domain of attraction, and the domain of attraction, of course, is it's the set of all initial conditions that converge upon the stationary points. So that is outside of this domain D subscript C, then our Lipinov potential function is strictly decreasing, but it's bounded below by 0. And so it cannot decrease indefinitely. And so therefore the parameter vector must tend to the invariant set. And going further, if the domain of attraction is equal to the whole set over which the ODE is defined, then we can say that the invariant set is a globally asymptotic invariant set. So looking at an example, here we have an associated ODE, and let's consider the Lipinov function of this form here. And then evaluating the time derivative of V along solutions of the ODE, then we see that that it's globally negative definite only if all eigenvalues of A are in the open left half of the complex plane. And so here we have a system that decays to a stable equilibrium point. So back to our analysis, therefore, if we consider the following definition for A, then our system stability is actually determined by the solutions of the characteristic equation of the homogeneous response. And as can be seen, so A has some significance in that it's actually a generalization of the reference correlation matrix. And the reason being is it takes into account the secondary path model as estimated in the input to the controller. So basically our analysis of the ODE boils down to studying the eigenvalues of A. So we'll considering the first order ODE with A, matrix A as defined, as well as the quadratic form of the Lipinov candidate function, then stability is globally assured by proving that this expression, where L is a non-zero vector, is globally negative definite. So one could think of this term as a series of ellipses defining the trajectories, and therefore L would represent the eigenvectors of the generalized autocorrelation matrix, defined on the principal axis of the trajectory space. So for brevity, I've removed some of the details of this covariance calculation. But looking at this final form here, we have this power spectral density, which is the power spectral density of the stationary process, L transpose phi. And so this form has some important ramifications. So firstly, in real situations, such as our A and C example, S is positive definite. And therefore, if the transfer function given here is strictly positive real, then we'll have this condition in 58 that the L transpose AL term will be less than 0. And of course, this corresponds to an exponentially decaying system, since the poles are in the left-hand side of the complex plane. And this actually assures that the equilibrium point will be stable. So yeah, I haven't addressed the boundedness condition on theta that's actually required by Jung's original theorem. I'll just leave it to say that since the filtered X LMS algorithm is linear in theta, that it turns out we can actually omit this condition. I won't go into the detail, but there's a reference here which shows those details for interested readers. And so finally, we can actually summarize the analysis of the ODE, and therefore the algorithm, LMS algorithm for the A and C problem as follows. So firstly, the transfer function is must be strictly positive real. The gain term must decrease to 0 as K updates tend to infinity. We also need to have a low eigenvalue spread on the input correlation matrix. It effectively says that we have an interesting reference signal. And then of course, we require the regularity conditions on the vector field. And so in this case, we have convergence in probability of the filtered X LMS algorithm for the A and C problem. And that's actually the end of the presentation. So that's all I had to say today. So we could probably have some questions now if there are any.